Today, I'd like to tell you about how we used some special properties of harmonic functions to design an algorithm for ray tracing a new class of surfaces. Formally, a function is called harmonic if the sum of its second derivatives is equal to 0, but the details won't matter too much for us today. You should just know that harmonic functions are a special kind of function which are very well understood mathematically. When people introduce harmonic functions, they often show an example like this, a nice smooth function with a characteristic saddle shape. But these pictures are kind of deceptive because many of the harmonic functions that show up in practice are actually a lot nastier, with various kinds of singularities where the function can blow up to infinity. And we'll see in a few minutes how singularities can cause all sorts of problems when we try to do computations with these harmonic functions. The particular computation that I'm interested in today is intersecting a ray with a level set of our function. So we start with some harmonic function f, an array at some point in space. Then we pick out our target level set, say the set of all points where f equals 0, and we want to find the first time when our ray intersects our level set. Once we can calculate these ray surface intersections, we can easily render level sets of harmonic functions directly. While this may sound kind of specific, it turns out that level sets of harmonic functions show up everywhere. To name a few examples, they show up in reconstruction algorithms like Poisson surface reconstruction or mesh repair with generalized winding numbers. They show up as shell structures in architectural geometry and space-filling surfaces in digital fabrication. They can be used as spanning surfaces for nonplanar polygons or for networks of space curves, and they also show up all over the place in math and physics, for instance as Riemann surfaces or hyperspherical harmonics. But despite their ubiquity, level sets of harmonic functions are hard to render with existing techniques. One problem is this fact that they may have singularities. This comes up, for example, in the implicit function used for surface reconstruction. If you try to find ray surface intersections with something simple, like ray marching with a fixed step size, you can easily tunnel through the surface, leaving behind gaps. If you try to run a more sophisticated algorithm, like sphere tracing using some purported Lipschitz constant, you get a smoother surface away from the singularities, but you still leave behind these big holes in your surface. For those of you familiar with sphere tracing, the problem here is that no valid Lipschitz constant exists around the singularities, so the method's guarantees don't apply. And of course you can try to fix this by decreasing your step size in ray marching, or increasing your purported Lipschitz constant in sphere tracing, and this may make things a little better, but it doesn't really fix the underlying issues, and so it still leaves us with these big holes in the surface around the singularities. Another big challenge is that level sets of certain singular harmonic functions may have boundaries. And so if you try to intersect rays with these surfaces, using standard root finding techniques like Newton's method or interval arithmetic or bisection search, you get all sorts of errors. The methods may converge to the wrong intersection, fail to find any intersection, or even converge to a spurious point outside of the surface, even for very simple surfaces. And if you try to run mesh extraction methods like marching cubes, or even fancier adaptive methods like whatever's happening inside of Mathematica's contour plot 3D, you run into similar issues and get spurious results outside of the desired level set. To get a better look at what goes wrong with existing methods and how we can fix things, let's take a closer look at sphere tracing. In its simplest form, sphere tracing is an algorithm to compute intersections with level sets of signed distance functions. Here, I've drawn the signed distance function for a curve in the plane, so at any point, the value of the signed distance function gives the distance to the curve, with a positive sign if we're outside the curve and a negative sign if we're inside. Now, if we have a ray and we want to compute its intersection with our curve, sphere tracing says that we should evaluate the signed distance function at our starting point, which tells us the distance to the closest point on the curve. And in particular, if we draw a sphere of that radius, the curve can never come inside the sphere because it never gets any closer than that distance. So we can step along our ray inside the sphere, stepping all the way to the boundary of the sphere, and we can be sure that we never accidentally cross the curve. We'll call this taking a safe step. Now we have a new point, we can evaluate our signed distance function again. This gives us another empty sphere, so we can take another safe step, and we just keep on going like this until our signed distance function tells us that we're close enough to the curve, at which point we return an intersection. And it turns out that it's easy to generalize sphere tracing beyond signed distance functions to a broader family called Lipschitz functions. You can think of these as functions whose gradient is always smaller than some constant L called the Lipschitz constant. And the important fact about Lipschitz functions is that the difference in value between 2 points can never be more than L times the distance in space between those points. So knowing the value of the function at a point provides a conservative bound on the distance to any other level set, which is exactly what we needed to run sphere tracing on these functions. and people have designed Lipschitz functions to encode some incredible scenes, like this iconic sphere trace snail designed by Inigo Quiles. But the problem for us is that many harmonic functions that people really care about are simply not Lipschitz. One illustrative example to think about is the angle function, often called atan2 when you're programming, which takes in a point and measures that point's angle with the positive x-axis. If we plot the angle function, it looks something like this. But now consider these 2 points whose angles differ by pi over 4. We can move them closer and closer to the origin without changing either of their angle values. No matter how close these points get, the function values never get any closer. So in particular, we cannot use these function values to get a distance bound for sphere tracing. The main idea of our algorithm is to get distance bounds from something known as Harnack's inequality for harmonic functions. If you have a positive harmonic function f defined on a ball, and say centered at some point x, then for any other point y inside this ball, Harnack's inequality gives us bounds on the value that our function can take at y. And the particular form is really not important right now. I'll go into more details later, but for the moment I just want you to see that we have these lower and upper bounds, depending on the radius big R of the ball, and the distance little r between our points x and y. And after a little bit of algebra, these bounds tell us that it's always safe to take a step of the following size if you're starting from the center point x. Even though our function is not Lipschitz, we can use the fact that f is harmonic to obtain a distance bound. And simply by using these distance bounds with the overall sphere tracing algorithm, you can already find intersections with level sets of some really nasty functions. Here's an example of computing intersections between an array and a level set of a harmonic rational function in 2D, where I've drawn the safe steps that our algorithm takes. That's the main idea. Now for the rest of the talk, I'll start by going into a little bit more detail about how Harnack's inequality works and where it comes from. Then I'll talk more about our algorithm itself. After that, we'll move on to looking at a few example applications. And finally, I'll discuss some thoughts about how all of this work can be extended. First, Harnack's inequality. As I mentioned earlier, Harnack's inequality bounds the value that a positive harmonic function can take at any point y enclosed in a sphere, based on the sphere's radius and its value at the center point x. And it applies in any dimension, although we'll mostly be interested in working in 3D space today. Pictorially, we can imagine that we have some harmonic function f plotted above the unit disk. Now we have this upper bound sitting above it, limiting how fast it can grow, and this lower bound sitting below it, limiting how fast it can decay. And these bounds are tight at the center point, where we know that the function's value is precisely f of x. At first, it may seem surprising that such a universal bound can even exist. After all, we just saw that harmonic functions are not Lipschitz, so they can grow arbitrarily quickly. So it's helpful to first consider a simpler case and just think about linear functions. Let's say we're working on the unit interval, and we have a linear function, and we know its value at the center. For concreteness, we can say that f of 0 equals 1. Now, a linear function can change arbitrarily fast. It can take on any value that you want at any other point. But if it changes too fast, then it does not stay positive anymore. Here we've made the function really steep, but that just means that its value quickly dips below 0. And the only way to fix this, to keep the function positive on the interval, is to make it less steep. So positive linear functions on the unit interval really must stay positive between their upper and lower bounds, otherwise they won't be positive anymore. Knowing that a function is positive gives you a lot of information about it. Now let's move on to more general harmonic functions. Let's say that we have a sphere of radius big R centered at some point x, and we know the values that our harmonic function takes along the boundary. As you may know, harmonic functions satisfy the mean value property, meaning that if we want to know the value at the center point x, all we have to do is take the average of the known values at all boundary points. And moreover, these boundary values pin down the values of our harmonic function at all other points inside the ball too. At any other point y with distance little r away from the center, the value of f is given by the integral of the Poisson kernel along the boundary, essentially just taking a weighted average of the boundary values now. And this formula lets you work out what your harmonic function must look like along the entire interior of the ball. Now, the key step needed to arrive at Harnack's inequality is just to observe that this distance between y and z, which appears in our integral, must always be at least big R minus little r, and it can be a most big R plus little r, just by the triangle inequality on this xyz triangle. And hence, so long as f is positive, the value of f at y must be between these two extreme values, where we replace the distance inside the integral by its maximum and minimum possible values. But now we're not taking weighted averages anymore, right? These weights are really just constant, and so we can pull them outside of the integrals. And once we do, we see that the integrals are now just taking the average value over the boundary again, which we know is precisely the value at the center, f of x. And that's it. That's Harnack's inequality. Of course, you can do a little bit of algebra to it to make the expression nicer, but that's really all there is to it. It's just saying that the value of our harmonic function at any point in this ball is a weighted average of the boundary values, and that the weights never get too big or too small. Now let's go into a few more details about our algorithm. Earlier, we saw that so long as f is positive on our ball, Harnack's inequality provides us with a safe step size. But there's just one little detail left. To use all this machinery, our function does have to be positive. Indeed, we saw that this positivity assumption is the key to the whole bound. But what if we want to visualize level sets of functions which are not positive? Well, it's easy to add a constant to our function to make it positive over the ball. So in order to find these safe step sizes, what you really need is a valid ball radius and a lower bound on the values that our function can take on this ball. And then we can simply add a constant to our function to shift it upwards, yielding a positive harmonic function on the ball, where Harnack's inequality applies and we can get a safe step size. And once we have these safe steps, our resulting Harnack tracing algorithm is pretty similar to sphere tracing. Starting from some point x0 and walking in direction d, we start by picking a ball radius on which our function is non-singular, then we shift f to be positive on that ball, and calculate a safe step size using the formula from the last slide. Then we take a safe step in the ray direction, and now we just repeat until our function value gets close enough to the target level set value. I won't go into the details of how you can derive valid radius and shift values, but it turns out to be pretty similar to computing Lipschitz bounds for sphere tracing, and if you're curious, we work through many examples in the paper. It really is important to use valid lower bounds here. If our shift c is invalid, meaning it fails to make our function positive on the ball, then rays may pass through the surface, yielding artifacts which become more and more severe as the bound becomes more and more invalid. Interestingly, the artifacts behave differently above and below the surface. They're worse for rays approaching from below, meaning the side where f is smaller than the target value, rather than above, the side where f is larger, since naturally the function won't need to be shifted as much in regions where it's larger. Also, in general, larger radii lead to larger step sizes, and therefore faster convergence to the target level set, as do larger shifts, where the c value is more positive. However, these two goals are often in conflict. In general, increasing the radius means that our function will take on lower values, leading to a smaller shift. On the left, we use a smaller radius, restricting our function to a smaller range of values, allowing for a larger shift. But by contrast, increasing the radius, as on the right, leads our function to take on a wider range of values, decreasing the shift that we can use. Obtaining efficient step sizes requires balancing these two considerations. But note that this is only about optimizing for efficiency. Our algorithm will return correct solutions whenever the provided shift value is any valid lower bound on the function value over the ball of your desired radius. And because our algorithm shares its basic structure with sphere tracing, we can also borrow acceleration techniques. For example, Keenan et al. Observed that the basic steps taken by sphere tracing are unnecessarily conservative. We know that our ray cannot intersect the target surface as long as it remains covered by our empty spheres. So rather than taking the conservative steps that sphere tracing takes, only stepping to the boundary of each sphere, we can actually take bigger steps, so long as our empty spheres still cover our ray. The only change required to the code now is that after taking each step, you have to check whether or not your empty spheres do cover the intervening segment of the ray. If they don't, it's easy to just fall back to an ordinary sphere tracing step, which is guaranteed to be safe. In some of our experiments, overstepping was able to basically cut the number of steps we had to take in half, and it's basically free. Another acceleration, which is more specific to our setting of harmonic functions, is to adjust the termination condition. In all these ray tracing algorithms, you have to decide when your ray has hit the surface. That is, when are you close enough to stop? And the easiest thing to do is to check if your function value is close to the target value. And especially with sphere tracing, when your function value really tells you your distance to the surface, this makes total sense. But for singular harmonic functions, it can be a bad choice. Take this function, for example, where I've drawn a few of the level sets, and we imagine we're trying to hit the black level set connecting the two dots where the singularities are. Here's the set of all points where the function value is within epsilon of the target value. you can see that it contains the black line that we're interested in, but the shape is really uneven. It gets really narrow near the singularities. If I draw a box of width 2 epsilon, you can see that we really don't fill it up. And so we're demanding unnecessary precision from our intersection routine. By contrast, if we weight this error that we're measuring by the gradient of our function, now the region of points where the error is less than epsilon is much more regularly shaped, and it really fills up the rectangle. Essentially, the problem here is that the error in function value has the wrong units, and we can use the norm of the gradient to really get an expression with units of distance, which measures the quantity that we're interested in. And this can make a huge difference, especially when approaching the surface at grazing angles or approaching the boundary of the surface. Of course, now there's a trade-off, right? Using the gradient in our termination condition decreases the number of iterations required, but it makes each iteration more expensive. In general, we found that this gradient termination often gave us a 10 to 20% speedup, but sometimes it actually made things worse. It really depends on what your scene is and how the rest of your ray tracer is set up. Finally, I'd like to take a minute to talk about a special class of harmonic functions, which we call angle-valued functions, that arise in a lot of applications. The prototypical example is the angle function itself that we looked at earlier. When I plot the function like this, it looks continuous, but that's of course just because I'm cheating and using a periodic color map. If I use a different color map, it becomes clear that the function jumps in value from negative pi to pi along the negative x-axis. But nonetheless, this function behaves in many ways like a continuous harmonic function, since it is indeed continuous when its values are viewed modulo 2 pi. In particular, although the graph of the angle function is discontinuous when plotted in this range from 0 to 2 pi, if we look at this function on any simply connected domain, like this spiral here, we can always find a continuous lift on this domain, which agrees with our original function mod 2 pi. And importantly, the mere existence of this continuous lift is enough to ensure that Harnack's inequality holds. Although we never compute this lift explicitly, its existence lets us compute safe step sizes for these discontinuous angle-valued functions. And in practice, we just have to look out for level sets above and below our current function value. For ordinary functions, we always consider the distance between the current function value and the target value f star, whereas in the angle-valued case, we're interested in f star plus any multiple of 2 pi. So we need to find the closest such level sets above us and below us, and make sure that we don't step past either one. But then, everything else works out pretty much the same. We just have to use Harnack's inequality twice to find 2 safe step sizes, one for each of these neighboring level sets, and then take the smaller of the 2 steps. One important impact of using angle-valued functions is that their level sets can now have boundaries. For example, if we look at the pi over 4 level set of the angle function, we see that it takes the form of this diagonal ray with a boundary point at the origin. And indeed, all of our examples of level sets with boundaries come from angle-valued functions like this, with singularities running precisely along the boundary curve. Now that I've discussed some of the more nuanced details, I'd like to emphasize that our Harnack tracing algorithm is still pretty simple to implement, even with all these additional features, and we were able to test it out in a lot of different places. We incorporated it into the PBRT ray tracer commonly used in rendering courses, we wrote WebGL shaders on ShaderToy, and even incorporated our method into Blender's ray tracer to obtain both real-time previews in Blender's editor, as well as polished renders with richer features like shadows and reflections. Now, let's take a look at some examples. One example, closely related to the angle function that I've been talking about, is the generalized winding number, also known as sine solid angle. Jacobson et al. Observed that you can take in an input mesh with holes, and fill in those holes with a smooth surface, given as a level set of the sine solid angle function. Here, we use Harnack tracing to directly render this level set, reproducing an example shown by Jacobson et al. Without having to perform the explicit meshing they used to show the results. The sine solid angle function actually defines surfaces filling in any loop in space, allowing us to visualize spanning surfaces for nonplanar polygons. Ordinarily, we think of sine solid angle as being defined for surfaces, where it measures the signed area of the projection of the surface onto the sphere. But it turns out that if you start from just a curve in space, and you pick any surface that has your curve as its boundary, then you will always get the same sine solid angle function modulo 4 pi, no matter which surface you picked. So we can really think about this solid angle function as a function determined by the curve itself. And then its level sets give us surfaces spanning the curve. For planar polygons, the 2π level set of the solid angle function provides the expected planar way of filling in the polygon, and it deforms continuously as the polygon is made less and less planar. And of course, by taking different level sets, we can adjust the convexity or concavity of this interpolating geometry. And this procedure yields a very general notion of nonplanar polygon. For instance, our polygons can have holes or even knotted boundaries, in which case the interpolating surface provides a cipher surface for the given knot. We find that the interpolating surfaces provided by the sine solid angle function have some really nice qualities compared with what you get from traditional approaches like generalized barycentric coordinates or subdivision surfaces. While almost all approaches give sensible results on nice inputs, like the ones in the top row, almost all cause overlaps even on simple planar non-convex examples as shown on the bottom. The only alternative shown here which doesn't suffer from these overlaps is using minimal surface for the boundary loops, but minimal surfaces have their own problems. It's well known that the minimal surface spanning some given boundary can jump discontinuously even when changing the boundary continuously. By contrast, our solid angle surfaces vary continuously, although they must then pass through a non-manifold configuration in the middle here. Solid angle also shows up in architectural geometry, where it's used to design architectural grid shells. And again, we can directly visualize these surfaces via ray tracing, bypassing the need for mesh-based optimization, which was previously required to construct these grid shells. In order to allow for perfect circular boundaries to these grid shells, we make use of explicit formulas for the solid angle of a disk and its gradient, which can be given in terms of elliptic integrals that are readily evaluated by standard numerical packages. In practice, we found that evaluating the elliptic integrals cost about as much as evaluating the solid angle for a 12-sided polygon, while providing considerably smoother results. We can also directly ray trace interpolating surfaces for point clouds, effectively visualizing the results of the classic Poisson surface reconstruction algorithm without requiring any volumetric meshing or linear solves. The key idea here is to follow the approach of Barrel et al. And to write the function in closed form as a sum of dipole potentials. This provides a closed form harmonic function, which is easy to evaluate at points or to bound over regions, and whose level sets can thus be visualized via Harnack tracing. As a more abstract example, we can use Harnack tracing to visualize Riemann surfaces. These surfaces play a key role in the study of complex analysis, but much of their interesting behavior happens around singular points, which are hard to resolve with standard techniques. We can accurately render them with Harnack tracing, and we can seamlessly combine them with traditional sphere tracing to illustrate the classic observation that Riemann surfaces look a lot like the spirals in parking lots. The key idea here is that you can think of a Riemann surface like this as the graph of an angle-valued harmonic function. And if we do a little rearrangement, it turns out that the graph of a 2D harmonic function can be written as the zero level set of a 3D harmonic function, so we can also apply Harnack tracing directly to render these graphs. As another example, we can visualize spherical harmonics. Spherical harmonics show up as the Laplacian eigenfunctions of the sphere, the spherical analog of sines and cosines. But they can also be viewed as the restrictions of certain harmonic polynomials in 3D space to the unit sphere, and we can use Harnack tracing to visualize the level sets of these polynomials, providing an alternative visualization of the different spherical harmonics. And moving up a dimension, we can also visualize hyperspherical harmonics, the generalization to the 3-sphere in 4-dimensional space. Here, the 3-sphere can be identified with ordinary 3D space using stereographic projection, and then we can apply Harnack's inequality in 4 dimensions to obtain safe step sizes for Harnack tracing. The main change is that now, the formula for a safe step size requires solving a cubic equation, rather than just the square roots required for ordinary 3D Harnack tracing. The other small tweak is that in this case, we have to account for the conformal scale factor from stereographic projection when measuring the size of our safe spheres. But we give a simple formula for doing so in the paper, and then the core algorithm proceeds exactly as before. One final example comes from digital fabrication. The gyroid is a triply periodic surface, which is often used for filling space inside of mechanical designs. Interestingly, the implicit representation of the gyroid is not a harmonic function in 3D, but we show that it can be seen as a slice of a harmonic function in 4 dimensions, which allows us to find safe step sizes and render the surface anyway. The key observation here is that the gyroid is a Laplacian eigenfunction. That is, taking its Laplacian yields a multiple of itself. And for any Laplacian eigenfunction in 3D, you can just write down the simple 4D function, which is harmonic in 4-dimensional space. So for any Laplacian eigenfunction, or even sums of Laplacian eigenfunctions in 3D, we can construct this 4D harmonic function and apply Harnack's inequality in 4 dimensions to find safe step sizes, letting us run Harnack tracing on all of these functions too. I'll also quickly comment on convergence. We showed that when using Harnack tracing, your rays converge to points on the surface at the same asymptotic rate as sphere tracing. To measure some results in practice, we explicitly meshed a level set of an angle-valued harmonic function in order to run sphere tracing against it, and we did indeed see the same rate of convergence for both sphere tracing and Harnack tracing, although the constant for sphere tracing was far better, and it required many fewer iterations overall. Finally, what's next? So far, I've been talking about harmonic functions f, where the Laplacian of f is exactly equal to 0. But one can also study subharmonic functions, where the Laplacian is always negative. And one can show that on any ball, a subharmonic function is always less than the harmonic function with the same boundary values. Similarly, one can study superharmonic functions, whose Laplacians are always positive, and a superharmonic function on a ball is always greater than the harmonic function with the same boundary values. And so, if we have upper bounds on harmonic functions, we can also apply them to subharmonic functions, since the value of a subharmonic function is upper bounded by the value of a harmonic function, which is at most the value of our given upper bound. And conversely, a superharmonic function obeys lower bounds on harmonic functions. So it's natural to ask whether we can apply Harnack tracing to functions like these. Such a procedure would be particularly useful, since if we have a function f whose Laplacian is bounded, say its absolute value is at most some constant lambda, then we can easily shift it down by x squared to obtain a superharmonic function, or shift it up by x squared to obtain a subharmonic function. So just like sphere tracing can be generalized from signed distance functions to more general Lipschitz functions with bounded gradients, Harnack tracing could be generalized from harmonic functions to more general functions with bounded Laplacians. Unfortunately, I haven't quite managed to make all of these bounds work out at this point, but I'm interested in continuing to work in this direction. More generally, we can move beyond just the Laplacian to talk about solutions to other PDEs. Harnack inequalities exist for many PDEs, not just Laplace equations, and so it's natural to try to extend Harnack tracing as well. And it turns out that the key issue here lies not in the inequalities themselves, but in the fact that the positivity becomes harder to enforce. If we start with a harmonic function, we can always add a constant to obtain another harmonic function whose values have been shifted up or down. But for most other PDEs, you don't have this freedom to add a constant shift, so it's harder to build up a general purpose algorithm which applies to the sorts of solutions to these PDEs that come up in practice, and not just to artificially constructive positive solutions. I'm also interested in optimizing surfaces represented as harmonic level sets. Sphere tracing has experienced something of a renaissance recently as one of the basic strategies for visualizing neural signed distance functions. However, there continues to be interest in alternative surface representations, in part due to challenges with enforcing the signed distance property. SDFs are usually optimized by enforcing the iconal condition that the gradient should have unit norm, which leads to non-convex, non-differentiable loss functions, and it's well known that this condition may still fail to guarantee that f is a true signed distance function. By contrast, harmonic functions are characterized by the simple condition that their Laplacian must be 0, which is a linear equation and arises from a variational problem. But one big open question is what spaces of functions should actually be optimized over in practice. Maybe there are explicit harmonic basis functions which would be convenient to work with, or maybe it's better to work in a larger space of implicit functions and try to impose this linear condition directly. I'm excited that our techniques have already started to be adopted in works on shape optimization and surface reconstruction, and I'm interested in seeing how much further they can go. Finally, I have many more questions about the solid angle function itself. It may be interesting to think more about the bounds we used on level sets of the solid angle function here. And there are two types of bounds of interest. One problem is bounding the spatial extent of level sets, meaning computing bounding boxes. Bounds on the position in space of these level sets are essential for incorporating Harnack tracing into existing renderers, which place objects into spatial hierarchies, so they don't have to test every ray against every object in the scene. In the paper, we showed that for certain well-behaved curves, the 2π level set is always guaranteed to lie within the bounding box of the curve. But clearly this is not true for all level sets, since some can really bulge far outwards. I'm curious about whether one can write down a bound which depends on the level set value to accommodate these other level sets as well. And also, there's still questions about computing lower bounds on the value of the solid angle function for Harnack tracing. We showed that when your curve is in some sense convex, then a shift of 4 pi always suffices. Explicitly, this shift works so long as your curve lies on the boundary of its convex hull. But I don't have a proof that this shift always works for general curves. I just know that I tried a lot of examples and never had any problems in practice. I'm also interested in evaluating the solid angle function in 4-dimensional space. One potential application of the solid angle function is shape interpolation. If we have two collections of curves in 2D, we can place them in 3D space, and then use the solid angle function to fill them in with a surface, whose slices give us planar shapes interpolating between our initial sets of curves. And the cool thing here is that exactly the same idea should work to interpolate between surfaces. If we have two surfaces in 3D space, we can place them in 4-dimensional space and use the 4-dimensional solid angle function to find a 3-manifold with our given boundary, and then we can take slices to obtain surfaces in 3D space, interpolating directly between our inputs. And we can use Harnack tracing to directly visualize these interpolating surfaces. But the reason I don't have a cool example to show on this slide is that I don't know how to evaluate the solid angle function in 4 dimensions. In 3D, there are nice closed form expressions for the solid angle of a triangle, but I don't know of anything analogous in 4D. The closest thing I've found so far is this complicated looking series approximation. But I'm still interested in thinking more about the behavior of the solid angle function in 4 dimensions. That's all I have to say. Thanks for listening.